Hello, my name is Maab, and today, under the title of Realizing Living Social Robot, Audio, Visual Cause, and Natural Response, I will represent my implementation. The outlines of this representation: first, I will discuss some issues and challenges faced the chit-chat systems, and the paper I used also, and the dataset and results, and finally the implementation. Uh, First issue I will talk about is the common knowledge base or the knowledge base the chit-chat system should aware during the human conversation, like when interact with the users. Like usually some new patterns or new entities uh, appear or added to the conversation. So the chit-chat system should be updated and use this new entities or new facts and add it to its knowledge base. So next time when this user use this fact or the during the conversation when we talk about related facts, the chit-chat system will master this knowledge like human beings, and it like has some sort of common sense knowledge. To do this, like we face the problem of memory and consistency because to make the chit-chat system learn all these new facts and already the stored in knowledge database, we need a lot of memory. And as we go through the conversation, we need memory. So as we go, the chit chat will start to forget the facts or the things we said in the first or in the past. So we need, like, we face also the problem of consistency. Third problem we have, like, to make the chit chat learn this new fact, we need a lot of training data, a lot of training example, like the same fact we add. So to solve this problem, like if we look like at this pipeline, if we are using our chit chat in real world application, so so during applications or the interaction with the humans, the chit chat system will like noting new entities or new objects or anything. So it adds this knowledge again to its knowledge base, and it should relate this new knowledge to or this new entity to the other entities we have and the relation we have. So we can introduce some sort of new fact. So this factual knowledge we gain through the conversation added the new entities, what we can call the knowledge graph completion, as we add new entities and relate these entities to the other relation we have. To do this during the application is very difficult because every new entity needs a lot of training example, as I said. So if we add a new example just during the application, we will have just one example, just one what the user responds. So we need an algorithm that can add new fact or new knowledge based on just one example per time. So this paper here discusses by using the one-shot rational learning for knowledge graphs, and it was like the first paper discuss this problem of one-shot learning for the knowledge graph. It tries to predict the new facts when we have only one training instance. So it uses a very famous dataset related to the knowledge graph, the nil dataset and the wiki dataset with some small modification. And instead of doing the embeddings, they use the pre-trained knowledge graph embeddings. So some models like 4 examples. So as we want to start with what is the knowledge graph exactly, the knowledge graph or the semantic network, as we can say it also, is like a network represents the real world entities. These entities could be object, events, situation, concepts, or anything else. It's try to represent this relation between them in a graph manner or a graph fashion. So it stores this information in a graph database and try like, that is why we call it knowledge graph. So we can say the knowledge graph like combine characteristic of several data models, because like it is a database, it is a graph, it is knowledge base. So it is database because we already have structured queries, and it is a graph because we can analyze it as any other network data structure. And we can say it, as it is already a knowledge base because like we can use it to interpret the data and infer new facts. So how the knowledge represent inside or expressed inside this graph, we can we express it like in a factual triples in form of the head, relation, and tail, consisting of the head entities, tail entities, and the relation between these entities. Or also we can call subject, predicate, and object, which what we call the resource description frameworks, the RDF, which is a famous famous method. And for example, if like we have Mike is a person, we have like here Mike is the head entity, person is the tail entity, and is the relation between them. So we put them in a tribal factual tribal form and present all these all these entities to each other. The knowledge graph processes can be like divided into 3 main processes. Like first, we have to represent this knowledge in the graph way. Then we have the knowledge acquisition. If we start like with the knowledge representation learning, where we try to represent entities and relations in knowledge graph in low-dimensional semantic space, which opens the way for like many knowledge acquisition tasks and downstream applications, like in real world. Also, like we can like categorize knowledge representation learning in 4 aspects. Like we have first the representation space we want to represent in. We have also the scoring function for the embeddings, and also we have encoding models. And finally, we have some sort of auxiliary information about these entities, which can help us to use the relation between these entities and add new entities also. So for the knowledge acquisition, next after the knowledge representation learning, we have which is a process where we try to extract or extract or organize this knowledge we have in the graph. So we can divide the knowledge acquisition like into 3 main tasks: the knowledge graph completion, and the relation extraction, and the entity discovery. We are focusing on the knowledge graph completion, where we try to add new entities and where we try to expand the existing knowledge graph already. So after we do the representation and acquisition, we will use it in real application now. So here comes the knowledge-aware applications, where we try, where it include a lot of applications like the natural language understanding, the question answering, the recommendation systems. Also in chit-chat system, when we try to analyze the user response. or understand the user response. All this come under the knowledge-aware application. So as we will focus on the knowledge graph completion come from the knowledge graph acquisition. The knowledge graph acquisition, like it aims to construct the knowledge graph from the unstructured text or other structured or semi-structured resources. Try to complete an existing knowledge graph and discover and recognize entities and relations. So recognized entities and relation could be like relation extraction, entity-oriented acquisition tasks such as entity recognition or entity alignment. And we will focus on the knowledge graph completion because the knowledge graph, by nature, it faces incompleteness. Like we always face missing entities in this graph. So knowledge graph completion is try to add new tribals to this knowledge graph and complete it. And it has some like sort of subtasks like the link prediction, entity prediction, or relation prediction. Here we will focus on the link prediction, which also is based on the embedding-based models. The link prediction it's the main task of the knowledge graph completion, and it's trying to estimate the likelihood or the probability of the existence of links between entities based on the current observed structure of the knowledge graph or the embeddings of the knowledge graph. Like in simple words, it takes the embeddings of the knowledge graph and try to estimate the likelihood of the new added entities are related to the already predefined entities in the graph. So link prediction can be like used across different KD knowledge graph. It could be used to predict the missing links between two same entities across the knowledge graph, or it could be also like used for entity alignment. So if we use it for knowledge, using it with the embedding-based models, we first taking entity prediction as example. Embedding based ranking method, it's first like we learn the embedding we first learn the embedding vectors based on the existing tribals, like the already predefined in the knowledge representation learning. Then by replacing the tail entity or the head entity with each entity, those methods could be used for like calculating the scores of all candidate entities and rank the top K entities we have. For the embedding, we use the method we mentioned in previously. And if we go through the methodology used here in this paper, first, the knowledge graph completion, as we know, the knowledge graph is represents the knowledge in collection of tribals. We have the entity set, and we have also a relation set. So the task of knowledge graph completion is either to predict the unseen relations between the two existing entities, or to predict the tail entity given the head entity and the query relation. So here they try to infer unseen facts for new added or existing long tail relations, where we have just only one training tribal is available, and we try to rank the true tail entity higher than other candidate entities. Given one example, this is in simple words the goal of this method. So the methodology is based on two parts. First, we have the neighbor encoder. Second, we have the matcher processor or matching processor. So the model here we use is based on the entity embeddings and the local graph structure. First, the entity embeddings we use from the predefined models. Then we have the local graph structure here, what we use here, the neighbor encoder. As the goal is to learn a matching matrix that can be used to discover more similar triples given just one example. So after that, the model will be able to predict a new relation using just one-shot link prediction tasks. So we use a knowledge graph, the neighbor encoder, to represent each entity with its local connection in knowledge graph. Like for example, here we have Leonardo da Vinci, and we have a lot of related entities, what we can call local connection. So in the knowledge graph, we try to represent each entity and the relations and the corresponding entity also. But here we focus on like the entity with its local connection and try to make a representation for all these group together for each entity. So like even we already like in the knowledge graph representation learning, we already like in these embeddings we made, we have some sort of relational information encoded in this embeddings, but like it is like proved that the structural patterns such as the passes we go through or we use, it is very beneficial for the relationship prediction. So that is why they use the local structure method. So they use a neighbor encoder to incorporate the graph structure, and they use the one hop neighbors, like just one neighbor per time, like for this local structure. But like if it's like one hop mean one relation per time. So the like painter here, its relation to another entity is not included here. So this is the one hop neighbors, and like for any entity, like for example Leonardo da Vinci, here we have we define its neighbor set as its relation and it's the entities we have in its local structure, and which all of it belong to our knowledge graph, and this is just the purpose what we want to do with the neighbor encoder. We try to encode the this neighbor set with its and like output a vector as a latent representation, which include all this information. So to do this, they face two the problem of like the encoding set sometimes have varying sizes, so that they use this function. First, it is invariant to the noise, and second, it is insensitive to the size of the neighbor set. So it gives a good result in giving the representation of the local graph structure. And they use also the activation function here is the hyperonic tangent function, and we have like in CRK and EK is a feature representation of the relation entity pair we have, and to encode this for every tuple like the RK and EK, we first use an embedding layer with a dimension like the dimension of the embeddings we use, and we get a vector representation of the relation and the entities. Then we apply it through a feed-forward layer, so we can encode the interaction with this tuple. Then if we go to, like, now we have the neighbor encoder representation. Now we need to go through the similarity matching process, which is based on like the, we see here is LSTM or RNN processor. Like for the matching processor, we have the neighbor encoder representation for the reference entity, the only example we have, and for the query entity, the one we try to predict. So we have like two vectors, like first these two vectors, this representation vector. So to get this similarity between the query and the reference, we use some rank among all the candidates or the entities we have. First, we simply try to concatenate the head entity and the tail entity into a single pair for every reference and for the query pair also, and try then to get the similarity between them using the cosine function. So if we just do it with just one step of cosine similarity, we face some sort of like the performance is not good, and it is very simple, so it is too shallow. So we need more similarity comparison. So we try to enlarge or try to empower this model by try to add the LSTM block and try to use the memory cell of the LSTM to do a multi-step matching, where every step in the matching process is defined as this. Here we have the LSTM, H is our hidden state, and C is the cell state. So S here we have S and Q is the concatenated neighbor vectors for the reference, and Q is the concatenated neighbor vector for the query pair. So after like K-processing step, we will use this score as find a similarity score between the query and the support entity pair. So for every query, by comparing it with the reference, by comparing the entities with the reference, we will get the ranking score. Among all the entities, we will have the higher ranking one. So as we use the future of learning, which is meta-learning fashion, our goal here is train the matrix that can be used to predict new facts with just one shot example. So the meta-learning here, we have training of tasks. So this task here, as we try to use a relation, relations in the knowledge graph, and we get like some patch of the training of this relation and call it the meta training set. And as we try to imitate the one-shot like prediction at evaluation time, where we have we just put one example or one triple in the training data set. So the matrix model can be then you used and tested by ranking the candidates that given the rest query and the label tribal in the training dataset, which contained just one example. And we use some sort of ranking loss function, which we have theta here represents the parameters of the matrix model. So this model, what they call G matching model, it like face some issues or some challenges, like first, we use some predefined models or predefined knowledge graph representation, which embeds an entities and relation into a low dimension structure. But like this structure have like about the size of it is a floating point vectors with size 100, and to use this like method for larger scale knowledge graphs, we will use required several gigabytes of memory space just for the embeddings we will use in the first step. As we have like a lot of the size of the embeddings is very large, we will need a lot of computational cost and training time. So like as here for our like even it's limited the performance of our model. Like here in our model, if I try to increase the neighbor numbers or the local structure area, like this area, how many neighbors we can have, so we can get more information about the entities and the facts, so we can predict the new entities with just one example, but like very well. So to do this, I try to change, like I used 200 neighbors per time. So I try to improve the promise. I try to raise it up until 500, but like it's stopped. We face some sort of memory limitation. So this method will like this problem of memory and computational cost, and we need a lot of training time, will limit this application or this technique in real world application, as like a large amount of space may be unavailable in real world scenarios. So and as we just use a limit number of neighbors, we use like for the local structure, the model will fail to capture more complex structure and relation here we have. So the idea is to try to compress these entities and relation embeddings into smaller size using some sort of dimensionality reduction, where we try like to compress the embeddings while try to preserving the information or the inherent information of the knowledge graph. So how we can like use what model we will use for dimensionality reduction. I proposed like a framework utilizes LSTM encoders. We try to obtain the compressed representation of the embeddings and try to reduce the memory size of the embeddings, and also try to improve the training performance without increasing the time complexity and reduce like the data storage we need. So why I use like the autoencoder, like the autoencoder usually used like for like it is famous for dimension reduction. It's also famous like for used for information retrieval a lot, because like they like have a good performance on it. And as our problem is some sort we can call similar to the information retrieval. We add new entity and try to go through all the data we have, so we can get the higher ranker entity, or candidate. So it is similar to the information retrieval, which the autoencoder is proved to be like very good for it. And as I deal with we deal with sequence or time series sequences, the LSTM was the best option to go with. So why I try to add LSTM, I add it before going to the neighbor encoder. Use a pre-trained knowledge graph embeddings I use already, which has like the size of 100 float like vector. So I tried to use the LSTM autoencoder and reduce this size into just 32 per embedding, and then we will try to to reduce all the embeddings. So if every process here will reduce the computational loss we have, and for the LSTM autoencoder, first the autoencoder is which a multi-layer artificial neural network, which incorporates the hidden units between the input layer and the output layer for internal representation learning, where we try to minimize the deconstruction error. It is used a lot for dimension reduction, and it is famous, as I mentioned, for information retrieval. So here the autoencoder, the LSTM autoencoder, allow this model to be used in both support variable length input sequences, so we can try to predict or output variable length out. We have sequences. Also, this the LSTM autoencoder is basis for many advances complex sequence prediction problems, such as text translation or speech recognition. So we use an encoder LSTM and decoder LSTM. The input to the model will be the embeddings of the knowledge graph and the encoder of the LSTM will read the input sequences step by step, and after this it's reading the entire sequence, we the hidden layer or the hidden layer try to represent an internal learned representation of the entire input sequence as fixed length vector, which we have here is 32. So this vector will then be provided as an input to the decoder model, where we try to interpret it as each step in the output sequence. The performance of the autoencoder is evaluated based on the model's ability to recreate these input sequences. So the LSTM here we use to try to learn the compressed representation of the sequence data. So the encoder can be seen as a list applying the count function on the previously constructed list and the new input. The decoder is try to unroll this list with a hidden to the output layer and extracting the element as the top of it, the most important one we need to reconstruct again. So but it use it in a reverse way. So the first element out is the last element in the encoder. For the LSTM encoder, use two LSTM layers to encode, and for the LSTM decoder, we use also two LSTM layers, and we use Adam optimizer for optimization, and we use the encoder, the LSTM, like is many to an LSTM, and also for the decoder, but the opposite for the decoder, we use one to many LSTM. This is data sets they use and the information about the data set. Wiki data set is very large and take a lot of time to run, or to when I pass it to the model. So I go with the nil data set for this implementation. For evaluation methods, I use the same as they use, which is common for the link prediction task, the mean reciprocal rank, and the hits, what we can call, which is a proportion of the correct entities in the top n ranks. As we do the ranking, in the top n ranks, we know the numbers of correct entities. So the function rank compares the scores of the correct triples among all the corrupted ones by replacing tail entities with other entities in the neighbor set, and large value of the mean reciprocal rank indicates a knowledge graph embedding model have capability on precise entity representation, while the hits on n denotes a rate of the head and the tail entities that rank within the top n ranks. Like here, we use the hits with n equal 1, 5, and 10. This is the result of the paper, as they use already. This is the predefined embedding models, and this is the predefined embedding models after they pass it to the model, the G matching model. So for the experiments we do in this implementation, we use the autoencoder. This is our main goal. We reduce the embedding dimensionality to 32. We use a nil dataset, and for the embed model, we use a complex one. I didn't change the max neighbor and the patch size and the number of the or the number of the patches we will go through. This is the result compared to the G-match model. Our model is very near, if we compare it with the mean reciprocal here, it is got more higher performance than the G-match, but for the first for the development set, for the test set, we get lower or for the mean reciprocal, we get lower performance or compared to the G-match. For also here we get lower results. Just the hits at n equal 10 get better in the sort of the when the embedding dimension is 32, but we can see that even we reduce the model huge, reducing, we use it, we reduce it 30% of its original dimension, but we get almost here we in the development set we get almost better result. In the test set we need more improvement, but we save a lot of memory here, and we make it more possible to deploy it on real time application. Also we can say the time we decrease the time like up to 25% of its original time. So this make it more reliable to real applications, and we reduce the dimensionality, the computational cost. In conclusion, using the LSTM autoencoder for the embedding dimension reduction, as I said, we reduce the memory up to 70% of its original dimension, which is 100. We also reduce the computational loss and the time. We speed the time up to 4 times compared to the original model. But for the testing, the performance is still behind the Gmatch, except the hits at the 10. So we need to improve it, I think, because the autoencoder still face some sort of loss. Due to time, I couldn't optimize autoencoder a lot. Also, the embedding dataset itself, if we change it maybe to Wikidata, can get good dataset. Like for future, first train the autoencoder at the same time as the Gmatch, because we train the autoencoder individually, and then try to use it for just prediction or just for reduction in the Gmatch, taking the output of the encoder. Then also we can change the position of the LSTM autoencoder. Like we can just put it after the neighbor encoder and try to see if it can get better results than reducing the dimensionality of the embeddings, the knowledge graph embedding. What about reduce the dimensionality of the local graph structure? So also need to try this method with the wiki dataset, but it is very huge and you need a lot of time for training. So this is my presentation for the implementation, and I will end my presentation here. Thank you.